So, projectile motion. It says here you might want to have a highlighter or a pencil as we go along here. Alrighty. Earlier we discussed the vector quantities velocity and acceleration. Since only horizontal and vertical motion was considered, we did not need to know about vector addition or the techniques of vector resolution. But for objects projected at angles other than straight up or straight down, we do. So what we're going to do now is we're going to take all the stuff that you've learned about dynamics and kinematics and vectors, and we're going to put it all together into the big daddy projectile motion. Because now we're dealing with two-dimensional motion. No longer is it trains and cars and bikes going forward, Fred and Barney and all that stuff. It's now things flying through the air in 2 dimensions. Okay? So a projectile is any object that is projected by some means and continues in motion by its own inertia. Cannonball shot from a cannon, a stone thrown into the air, or a ball that rolls off the edge of the table are all projectiles. These projectiles follow curved paths that at first thought seem rather complicated. However, these paths are surprisingly simple when we look at the horizontal and vertical components of motion separately. The horizontal component of motion for a projectile is no more complex than the horizontal motion of a bowling ball rolling freely along a level bowling alley. I'm going to read that again. The horizontal component of motion for a projectile is no more complex than the horizontal motion of a bowling ball rolling freely along a level bowling alley. So what they're saying is, and even if you think about that picture that I showed you, the horizontal part of that motion is exactly the same as if it was just rolling along the ground. Okay? It just happens to have a vertical component built in as well. If the retarding effect of friction can be ignored, the bowling ball moves at a constant velocity. Highlight that one. Highlight that one. The bowling ball moves at a constant velocity. Highlight, not stroke it out. I'm not sure what I did there. Constant velocity. It covers equal distances and equal intervals of time. It rolls of its own inertia with no component of force acting in its direction of motion. There is no force. If you look back at the picture here, after the ball is in the air, what forces are acting on it? Gravity down and a little bit of air resistance. The guy's already thrown it, right? Doesn't matter how much he leans, right? Doesn't matter. You can't put any English on the ball. It's not going to matter. There's no more forces acting, right? Now, in fact, if you take that rule that I gave you, if you measured the distance horizontally between the balls, you should find that they're always what? Darren, I need you to listen because I'm telling you important stuff. If you measured the horizontal distance between the balls, okay, so I'm talking about like this. If you measured this distance from there to there, and from there to there, and from there to there, they should always be the same. The horizontal distance should always be the same. Okay, because the ball does not slow down horizontally. I'm going to say that again. The ball does not slow down horizontally. It slows down as it goes up, vertically, and it speeds up as it comes down, but the horizontal component of the speed should do what? Remain the same, neglecting air resistance, of course. Okay? So, it covers equal distances and equal intervals of time. It rolls at its own inertia with no component of force acting in its direction of motion. It rolls without accelerating. The horizontal part of a projectile's motion is just like the bowling ball's motion along the alley. Interestingly enough, the horizontal component of motion for projectile is completely independent of the vertical component of motion. The X and the Y components are completely independent. It does not matter how fast it's going vertically, it's still going to go exactly the same speed horizontally. Each one acts independently of the other. Their combined effects produce the variety of curved paths that projectiles follow. It's an example of vector addition. The multiple flash exposure figure 2 shows equally timed successive positions for a ball rolled off a horizontal table. Investigate the photo carefully, for there's a lot of good physics there. The curved path of the ball is best analyzed by considering the horizontal and vertical components of motion separately. There are 2 important things to notice. The first is that the ball's horizontal component of motion doesn't change as the falling ball moves sideways. The ball travels the same horizontal distance in the equal times between each flash. That's because there's no component of gravity acting horizontally. Gravity only acts which way? Vertically. Gravity acts only downward. So the acceleration of the ball is downward. The second thing to note in the photo is that the vertical positions become farther apart with time. The distance traveled vertically are the same as if the ball were simply dropped. It's interesting to note that the downward motion of the ball is the same as that of free fall. And if you look carefully here, I'm going to explain this to you. Okay? This ball right here has been dropping for exactly the same amount of time as that one. And where are they in the air? Exactly the same spot. And this one right here, exactly the same spot. So does it matter that this one was fired sideways?
Yep.
Or will they land at exactly the same time?
They actually.
Hmm?
Seriously, they will. If you chuck the ball like this, and you drop on
The
it.
path traced by a projectile that accelerates only in the vertical direction while moving at a constant horizontal velocity is called a parabola. You should know that word.
That's amazing.
When air resistance can be neglected, usually for slow-moving projectiles or ones very heavy compared to the forces of air resistance, curved paths are parabolic. So here's your first question. At the instant a horizontally held rifle is fired over a level range, a bullet held at the side of the rifle is released and drops to the ground. Which bullet, the one fired from downrange or the one dropped from rest, strikes the ground first? The one that's dropped straight down or the one that's fired out? Which one hits the ground first? And those are your choices. Both bullets will land at the same time. In fact, Mythbusters has proved it. This is one of the very few instances where the Mythbusters boys actually proved the theory.
No. Let's see.
They will land at the same time, Justin. You go right ahead and believe in that, whatever you like to think. Same time. I'm going to assume this is you.
No, I don't see it.
Upwardly moving projectiles. Consider a cannonball shot at an upward angle. Pretend for a moment that there's no gravity. Then, according to the law of inertia, the cannonball will follow the straight line path shown by the dashed line in Figure 3. So if there's no gravity, it's just going to go straight like that, right? But there is gravity, so this doesn't happen. What really happens is that the cannonball continually falls beneath this imaginary line until it finally strikes the ground. Get this, the vertical distance it falls beneath any point on the dashed line is the same distance it would fall if it were dropped from rest and had been falling for the same amount of time. This distance is given by d equals 1/2 gt squared, and that of course comes from the formula d equals vit plus 1/2 at squared, where t is the elapsed time. And this is what they're saying there. They're saying is that if I were to drop the ball from that height, if I were to drop it after 1 second, it would have fallen 5 meters. And if I were to drop a ball and let it fall 2 seconds, it would fall 20 meters. If I were to drop a ball and let it fall for 3 seconds, then it would drop 45 meters. The point on the parabola is the point that far below that imaginary line where it would have fallen even if it wasn't moving up. This would have an initial vertical velocity of 0. It would fall that same distance even though it's already moving up. The vertical is independent of the horizontal. We can put this another way. Shoot a projectile skyward at some angle and pretend there's no gravity. After so many seconds, t, it should be at a certain point along the straight line path. But because of gravity, it isn't. Where is it? The answer is it's directly below this point. How far below? 5t squared, or 4.9, right? Minus half of 9.8. Isn't that neat? I should have a question in there. Isn't that neat? And you answer yes. Note another thing from Figure 3. The cannonball moves equal horizontal distances in equal time. This distance from there to there is the same as that distance from there to there, and is the same as that distance from there to there. It moves horizontally the same distance in 1 second. That's because no acceleration takes place horizontally. The only acceleration is vertically in the direction of Earth gravity. The vertical distance it falls below the imaginary straight line path during equal time intervals continually increases with time. Figure 4 shows vectors, you don't have to put the page. Figure 4 shows vectors representing both horizontal and vertical components of velocity for a projectile following a parabolic path. Notice that the horizontal component is everywhere the same and only the vertical component changes. Here's the vertical. Here's the vertical. There is no vertical there. Okay, the red one constantly changes. The blue one is always what? The same. Okay, and we use that when we're trying to predict where things are going to land. Note that the actual velocity is represented by the vector that forms the diagonal of the vector formed by the vector components. Here's my blue, here's my red, and when I add them together, tip to tail, well, it's not going to let me do it. I get that diagonal, which is the instantaneous velocity at that point. At the top of the path, the vertical component vanishes to 0, and so the actual velocity there is the horizontal component of velocity at all other points. Everywhere else, the magnitude of the velocity is greater, just as the diagonal of the rectangle is greater than that of the sides. Figure 5 shows the path traced by a projectile with the same launch speed but at a steeper angle. Notice that the initial velocity vector has a greater vertical component. Here it is here again in red. Right? The blue one is shorter. This results in a higher path, but the horizontal component is less, so the range is less. This is what we call the range right here. Okay? The range is how far it goes. And if you happen to be a military guy that's in charge of bombing or something like that, then figuring out the range is kind of important.
Yeah.
The range. Just keep firing until you hit it.
Yeah.
Figure 6 shows the paths of several projectiles all having the same initial speed but different projection angles. The figure neglects the effects of air resistance, so the paths are all parabolas. Notice that these projectiles reach different altitudes or heights above the ground. They also have different horizontal ranges or distance traveled horizontal. So if you go 75, then it goes up high, right? 60, 45, 30, 15. Do you notice anything kind of odd about that diagram?
Yeah.
What do you notice about those points that I just circled?
Hey.
There's two ways to get there.
75 is 15 degrees from 90, and then 50 degrees is 50 degrees from
Yep.
0.
75 and 15 are complementary. They add up to 90, as are 60 and 30. The remarkable thing to note from figure 6 is that the same range is obtained from two different projection angles, angles that add up to 90 degrees. An object thrown into the air at an angle of 60 degrees, for example, will have the same range as if it were thrown at the same speed at an angle of 30. For the smaller angle, of course, the object remains in the air for a shorter time. Now that tells us that if you're trying to throw something really far, what angle should you use?
45.
45. Now that is only true if there's no air resistance. Maximum range is attained when the ball is batted at an angle of nearly 45 degrees. In cases where the weight of the projectile is comparable to the applied force, as when a heavy javelin is thrown, the applied force does not produce the same speed for different projection angles, and maximum range occurs for angles quite a bit less than 45. So heavy things like javelins, you want to throw at less than 45. Lighter things, baseballs, compared to the force, if the force is considerably greater than the weight force of it, then 45 is your number, right? If it's heavy, though, you don't want 45, you want something less. We've emphasized the special case of projectile motion without air resistance. When there is air resistance, the range of projectile is somewhat shorter and is not a true parabola. This is what I was talking about with the ball in the garbage can. Because of air resistance, it does that. And in fact, I think you can clearly see here, this distance, right? This distance here is less than this one, isn't it, right? And that was a question that we had.
You said that.
Is that what we said? We're pretty smart, Justin. Okay. Have you been listening? A projectile is shot at an angle into the air. If air resistance is negligible, in other words, if you don't worry about it, what is its downward acceleration? And I need a number. What's the answer? Minus 9.8. Gravity, downward acceleration. Now, did somebody put 9.8?
Yeah.
Yeah? Okay, so it should be negative, right? Should be negative. Okay. Now, what is its horizontal acceleration? Answer? 0. Horizontal acceleration, 0. It travels at a constant velocity sideways. Constant velocity, the acceleration is 0.
I told you.
At what part of the path does a projectile have minimum speed? Where is the speed the smallest? A, B, C, or D? Where is the speed the smallest? Correct answer is C, at the peak, right there. Why is it traveling the less? Well, because here it only has the horizontal component. It only has a horizontal component here. Here it's got horizontal and vertical, and the horizontal is the same all the way, so any vertical is going to increase the speed, right? So it's traveling at its smallest speed, right? Okay, last little bit here. If air resistance is small enough to be negligible, a projectile will rise to its maximum height in the same time it takes to fall from that height to the ground. In other words, the time up is going to be the time down. Guys, give me like 1 more minute. Calvin. This is because its deceleration by gravity while going up is the same as its acceleration by gravity while coming down. The speed it loses while going up is therefore the same as the speed it gains while coming down. So the projectile rises at the ground with the same speed it had when it was projected from the ground. In other words, if you fire a rifle straight up into the air, you better get out of the way because how fast is it coming down? The same speed that it left the rifle. And you wouldn't stand in front of a rifle.
They did that too. They busted it. It gets like air resistance.
Yeah, the air resistance, yeah, dramatically, right? Yes, I know, I've seen that one, yeah. If an object is projected fast enough so that its curvature matches the curvature of the Earth, and it's above the atmosphere so the air resistance does not affect its motion, it will fall all the way around the Earth and become an Earth satellite. We talked about this in grade 11, right? If you can fire something fast enough, like this,
Oh, yeah.
right, then it will simply continue to orbit.
Let's try.
Geosync orbit.
Yeah, might be a little tricky. Okay, let me see if I can get